Okay, so in this episode, we will discuss the finite volume method of CFD. So let's read the question. The figure below shows a large plate of thickness 2 centimeters and has a thermal conductivity and some heat generation. Faces A and B have temperatures of 100 and 200 respectively. Okay, so they assume one-dimensional. So this is a one-dimensional problem. Okay, this implies that it's one-dimensional. So it doesn't matter. Y doesn't matter. Z doesn't matter. So calculate the steady state heat distribution. Okay, with the finite volume method and the central differencing scheme. So compare the, okay. So we're expected to use the finite volume method and the central differencing scheme. So let's have a look. We have the differential equation here. Now, just as a side note, let's identify what terms are these. This involves a second derivative with respect to space, right? A second derivative. See, there's one derivative here, and then another derivative here. Second derivative with respect to space. This means this is a conduction term. So this is conduction. And then if the term is not temporal, if it's not conduction, if it's not convection, so this term is not temporal because it doesn't have a ddt. It's not convection because it's not a first derivative with respect to space, so it's not ddx, and it's not conduction because conduction is over here. So therefore, this is a source term. Okay, so this is a source term. Okay, so the way we approach this is different from the last tutorial. In the last tutorial, we learned the central differencing scheme. So the central differencing scheme requires us that we take y2 minus y1 divided by the segment. Okay, in this approach, we're going to use the finite volume method, so FVM. So how is it different? In FVM, we consider each of the segments as a control volume. Yes. So this grid you see here, all of these are control volumes. So this is a control volume. This is another control volume. This is another control volume. And so fluid is entering and leaving these control volumes. Okay. In this case, it's not fluid because it's a solid plate. So it's a heat that's flowing into the control volume and leaving the control volume. So in the last tutorial, the central differencing scheme uses y2 minus y1 divided by the segment. In this method, the finite volume method, we are going to integrate over the control volume. We're going to integrate over the control volume. So how are we going to do that? So just like normal, first we consider the internal nodes. So let's take a look at node 2, 3, and 4. Okay, so 2, 3, and 4. So at 2, 3, 4, we have the template. So let's draw the template. So we have P, east, west, small east, and small west. Okay. Now, what are we going to do here? So let's go ahead and start with the differential equation. So with this differential equation, copy it. We have okay. So we're going to integrate over the control volume, right? The control volume is this. Okay, from small west to small east. This is one control volume. Okay, and then this side is the neighboring control volume. This side is another neighboring control volume. Okay, so let's forget about these two. We're going to integrate over this segment. Okay, here. So let us do that. Go ahead and integrate this. All terms we integrate with respect to x. So dx, dx, dx. And then we're going to integrate from west to east, west to east, west to east. So now let's go ahead and integrate each term. So let's take a look at the first term. The first term requires us to integrate this. Now this is actually pretty simple. Notice that there's a derivative term and then there's an integral term. So you see, derivatives and integration are opposite effects, right? They're opposite effects. So this integral will cancel with this derivative, okay? They will cancel each other, right? Because they're opposite effect. It's just like saying you put it on fire and then you put it out with water. Okay, so it just gets you back the original thing. So they cancel, leaving you with this. So what are we gonna do? We're gonna take this, just copy it down. Then we have this thing evaluated at east. Same thing evaluated at west. So you might ask me, well, what's this evaluated at east, evaluated at west? So it's basically just like normal integrals. Let's say I give you an integral, for example, integrate x squared dx from 1 to 2. So how would we do this? We take, power plus 1 divided by new power. Then we go evaluate this at 1, evaluate this at 2. So what you're supposed to do, you sub 2 into there, minus away, you sub 1 into there, right? So it's basically this, where you sub x equal to 2, minus away, the same thing, but you sub x equals 1. See, it's the same thing. So think of this thing as the east. This thing is evaluated at east. Sorry. Let me say that again. This thing is evaluated at east. This thing is evaluated at west. Same thing. See, this thing is evaluated at east, and this thing is evaluated at west. Okay, so that's what we're doing here. That's how I get this east minus west. Okay, then you look at this. Q is just a constant. It's just a number. Q is just a number. So this will actually evaluate to Q delta x. Okay, so let me explain why is this the case. If you think about this, let's consider this. Integral west Q dx. Okay, Q is just a constant. A constant is just a number that stays still. It won't change. It's not a function. So let's say I give you, for example, this. So 2 dx, right? 2 is a constant also. 2 is a constant. So let's evaluate this from west to east. So this would be 2. So integral of 2 would just be 2 and then x. Then we have to evaluate this at east minus evaluated at west. So this would be 2 x e minus x w. So this is x at e and x at w. Okay, so let's get rid of this. Okay, so the same thing here. Q just treat it as a constant. So the integral of a constant is you take that constant, you put x to it. So this would be Q x east west. So you take the same thing, but this is x at the point E minus x at the point west. Okay, and let's have a look. What is this thing? Let's go back to the diagram. See? Let's have a look. This is x east. This is x west. So xe minus xw is actually the distance between them, right? Which is delta x. Okay, so this x east minus x west is actually delta x. Okay, so this is actually the x. That's why if I know straight away, I see a constant and then I integrate it from west to east, integral of a constant from west to east, I'll know it's just the interval. It's just from west, the distance from west to east, which is delta x. Okay, so that's how I got this straight away. Okay, then integral of 0 is just 0. Okay, because it's like finding the area under a graph which is 0, which is just it's just 0. Okay, so let's have a look. Can I simplify anything? Yes. K is constant throughout this problem. Okay, K is constant, so I can factorize this out. Okay, so I have dtx at east, dt dx at west. Okay, plus q delta x 0. Yeah. Okay. Now, what are we going to do here? So, this is where we use central differencing scheme. So, okay, so this is where we use central differencing scheme. And let's go ahead and use that. So, we want to find dt dx at east, correct? So, we want to find dt dx at east. So, since we're looking at east, let's stand at east And then remember from the last tutorial, if you want to find this derivative, it is the immediate right minus the immediate left divided by the segment. Okay, so to the right we have east, to the left we have p. Then the segment is delta x. Okay, so this is actually pi e minus phi p divided by delta x. Okay, then we also need dt dx evaluated at west, which is, okay, now let's take a look at west. We stand at west, and then we look. To the right of west, we have p. To the left of west, we have big W. So this is this divided by delta x. Okay, now we're going to sub these two results, this result and this result, we're going to substitute it into here and here. Okay, so let's go ahead and do that. Let me just take a look at my book. TE minus TP delta x minus TP minus TW divided by delta x plus Q delta 0. Okay, now uh we're gonna simplify this. So let's take a look at how to simplify this carefully. Okay. So notice that both this fraction and this fraction have a denominator of delta x, right? They have a denominator of delta x. So we're going to factorize it. Okay. We're gonna factorize delta x, and then we're gonna put it outside the bracket. Okay, put it outside the bracket. So what would that look like? That would look like this. So k delta x, and then all we're left is are the the numerator terms. The numerator terms. Okay, all we're left is are the numerator terms. So let's go ahead and simplify that. So you see, negative TP minus TP is minus 2 TP, right? Minus 1 is minus 2. And then negative times negative will give me positive. Okay. Next, we're going to expand this term. So this expanded to here, and to here. So we'll just multiply everything out. So we have k. Okay. Now we're going to substitute all the values. Okay. So sub in values. So we're going to calculate all the terms that we see here, and then we're going to substitute in. Okay. So let's have a look. So remember the whole length, the whole thickness of the wall is 2 cm, right? 2 cm. So to calculate W, and then we discretize it into 5 grids, correct? Let me show you. So you see, 1, 2, 3, 4, 5. So we cut the 2 cm into 5 equal pieces. Therefore, delta x is given by 2 cm, which is 0.02 meters, divided by 5, which is 0.004 meters. Then we want to look for k delta x, right? Because we have k delta x here. K delta x is given by 0.5 divided by 0.004, which is 125. And 2k delta x is just twice of that, right? It's twice of the same thing that we got. Let me just write this out. 2 times 0.5 divided by this, which is 250. And then we also need the last term here, right? So this is q delta x. Q delta x. So the value of Q they told us is 1000 kilowatts, okay? Kilowatts, don't forget the kilo. So 1000, and you have to account for that kilo. So kilo is 10 to the power 3. So kilowatts times delta x is equal to 4000. Okay, so now we can substitute all those numbers in. If you do that, you will get 125 TW minus 250 TP plus 125 T east. Okay, so now that we have the general template for the internal nodes, which is nodes 2, nodes 3, nodes 4, we can use this and substitute it in. So what do I mean? So let's have a look. Let's have a look. Okay, I need a clean version of this. Okay, so okay, so in the middle we have P. To the right we have east. To the left we have west. So remember, I'm gonna take this template, then I'm gonna put it over point two. Okay, so at if I put the template here, then let me just show that again. Let me just shift this above. So if I put the template over 2, that means P becomes point 0.2, big E becomes, sorry, I should make this bigger. I should make this bigger. Okay, so, you see, if I put this at point 0.2, then P is point 0.2, big E is point 0.3, big W is point 0.1. Okay, so knowing that, what we do is, we take this equation, and then we substitute the values in. So this becomes T2, this becomes T uh 3, and this becomes T1. And then now you transfer the template. So from this way. So what I'm gonna do is now I'm gonna put position P on top of 3. So this P will be on top of 3 now. So in this case, see, east is 4, P is 3, west is 2. Okay? So one of the equations you get is this first one. Okay? Next, we use this again. So remember, in this case, now P is 3, east is 4, west T, T, west is T2. So now you generate this equation, 125 T2 minus 250 T3 plus 125 T4. Okay, and then we will do the same thing. We'll get rid of this. Okay, so now we move this template over, put it over 4. Okay, so now P is 4, east is 5, west is 3. So P is 4, east is 5, so T5 is T4, and west is T3. Then you'll generate this equation, 125 T3 minus T5, 250 T4. Okay, so let's check if we got this. Yeah, it's equivalent. Okay, so in the solution, what they did is just an opposite sign. So it's the same thing. It's the same thing. So what my version is just times -1 and this side times -1, which is equivalent. So it doesn't matter if it's the 125 T1 minus 250 T2 plus this. Like my order of signs, the negatives and the positives, or their orders of sign. Okay, as long as they're row equivalent. This is what you call row equivalent. They're the same thing. Okay, so my answer is correct. Okay, so we already managed to get this tree. Now we have to look at the boundaries. Okay, so let's get the boundary equations. So to get the boundary equations, let's have a look. Let's draw the boundary first. So at this edge we have TA. which is 100 degrees Celsius, right? Half a distance away, half a distance we have zero point 0.1, half a distance we have zero point 0.2. Okay. Okay. So we will always use this differential equation. So after, we don't need to repeat the process over and over again. Let us use this equation, okay? Let's call it star. So we will always use this equation star to draw, to write out the linear equation, okay? So always reuse this equation. Let's go back down. Then reuse star, okay? So let's see. So star is given by this, right? I'm just copying star, equation star down. Okay. So now we have to find this and this at the boundaries again. So let's take a look. First, let's draw the general template over it. So we have point P here, small east, big east, small west, and there is no big west. Okay, there's no big west because it's outside the domain. It's outside the domain. So let's have a look. So let me bring this down a bit. So we want to find d phi dx at east, correct? So we stand at east, then we look to the right minus to the left divided by the segment. So to the right we have east, to the left we have this. So this is phi e, this is phi p, and the segment is delta x long, right? Delta x. So this is actually phi e minus phi p divided by delta x. Then now we want to look at d phi dx evaluated at west. So if you stand at west, you see, there's no left, right? There's no left. So that means we have to use the forward differencing scheme, the forward differencing scheme. So we cannot use left, so we have to use the point itself. We have to use W itself as one of the points. So remember, normally to find derivatives is uh immediate right minus immediate left, but we don't have immediate left, so we have to use the point itself. So immediate right minus the point itself divided by the interval. So you see, immediate right is phi p. So we don't have the immediate left, so we're gonna have to compromise by using the point itself, which is phi w. Then the segment is delta x over 2. Delta x over 2. Okay, so it's delta x over 2. So d phi dx at west is actually phi p minus phi w divided by delta x over 2. And then I'm just gonna straight away simplify here. So times 2 times 2. So this will be actually 2 phi p minus 2 phi w over delta x. Yeah, because this 2 can cancel. Okay, so take this and then take this and substitute it into the differential equation, which is here and here. So what we get is, let me check my solution. So we have this minus this divided by x minus. Okay, so now let's go ahead. Let's factorize this out. Factorize it. So it will come out to the bracket. And then we simplify the numerator. So simplify the numerator. What do we get? So you see, minus 1 minus 2 is minus 3, right? Minus 1 minus 2 is minus 3. Then negative times negative will give me positive. Okay, so let's go ahead and expand this bracket. Okay. Okay. So now we need to calculate this, right? We need to calculate this. So 3k delta x is equal to 3 times the conductivity divided by the distance is equal to 375. Okay, so I'm gonna substitute every value in, substitute, 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 and rearrange the equation. So I'll get this. Okay, so remember that this is T small west, and small west is actually the boundary. You see, small west is the boundary, and we're given that boundary is TA. TA is given to be 100 degrees Celsius, right? That's the boundary condition that they give to us. Yeah, this is TA. So we're gonna use that and substitute it in. So this is actually 100 degrees Celsius. So this is 2500. Sorry, 25,000. 25,000 plus 4,000 is 29,000. 29,000, you bring it to the other side, will become negative 29,000. So what we're left will be T. Okay, let's also simplify this. So you see, what is TP? What is TP? So we're looking at this diagram here, right? TP is actually T1 and TE is actually T2. So we'll replace this. This is T1, this is T2. So at the end of the day, you simplify everything, you should get let me check here. Oh, sorry, I think I wrote something wrongly. Yeah, I wrote this wrongly. It should be 375. Yeah. And then again, at the end of the day, you should get this, which is correct, except the answer provided it in the opposite sign, right? The answer provided plus, minus, and plus here, which is okay. It is the same thing. So this is correct. Okay, now we have to find the last equation at the other boundary. So let's draw the diagram. So this is B, which has a temperature of TB. Then half a distance away we have 5, and a full distance away we have 4. Okay. Then let's also draw the template. So the general template will look like this, right? Because we're looking at 0.5, so P is 0.5. This is small east. This is big west. This is small west. Yes? Okay. So now let's again reuse the equation star. So reuse star. What do we have? So I'm just gonna copy down star. Okay. So now we have to find dt dx at east, dt dx at west. So let's find this first at east. So what we do is we stand at east and then we look. So see, remember, derivative is given by immediate right minus immediate left divided by the segment. But we don't have the immediate right. Okay, so that means we have to use the backwards differencing scheme. So we don't have immediate right, so that means we have to use backwards differencing scheme. So if we don't have the right, we have to use the point itself. We have to use the point itself. So instead of immediate right minus immediate left, it'll be the point itself minus the immediate left divided by the segment. So the point itself is phi e minus the immediate left, which is phi p, divided by the segment. So the segment is delta x over 2. Okay, if I take top and bottom times 2, this and this cancel, and then the top would distribute to become like so. Okay, so now we also want to find the west version. So we want to find this. So immediate right minus immediate left divided by the segment. So immediate right is by P, immediate left is by W, divided by the full segment, which is delta X. Okay, now we will substitute this result, substitute it into these two. Okay, so we have, okay, okay, uh, factorize these two. Sorry, let's go ahead and simplify the numerator, right? So the numerator, what do we have? In the numerator, we have minus 2 minus 1, which is minus 3, right? Minus 2 minus 1 is minus 3. Then we have negative times negative will become positive. Okay, so next we want to distribute. So take this, distribute, distribute, distribute. Then we have 2. Okay, but remember, what is T small east? T small east is actually the boundary condition, right? You see, this is small east, this is small east, and it's actually TB. And TB, they have already told us, which is 200 degrees Celsius. Okay, so this is actually TB. Okay, so let us substitute all the values that we know. So this is 250 times 200 minus 375. All these values I have obtained from the previous questions, okay? So take note of that. 125 E4 plus 4000 equals to 0. And if you rearrange this whole thing, rearrange them to the right positions, you should get 125 E4 minus 375 T5 is equal to this. So yes, let's check the solutions. Yes, okay. So we've already obtained this, and this we've already obtained it, right? The 29,001, which is which is yeah, this equation. So we've obtained all the equations. So we have five equations and 5 unknowns. For the 5 unknowns, we have T1, T2, T3, T4, and T5. 5 equations, 5 unknowns. T1 to T5 are solvable, and therefore this problem is complete. So as long as you can get all these equations, these 5 equations, your problem is done. Okay, so we're done with this. If you found this video helpful, please donate me on Payla or Coffee to help the channel grow. Thank you very much.